Okay, so this is the solution video for paragraph 3, and this is actually a problem that we did in class, so if it looks familiar, that's why. So we have a puck of mass MP sliding across a horizontal surface and colliding with a stationary non-uniform rod that's pivoted about its left end in the three figures as shown. So in each case, the puck travels with the same initial velocity, Vp, and collides with the rod at a time, Tc. In case 1, the puck rebounds. In case 2, the puck comes to rest. And in case 3, the puck sticks to the rod. Oh my goodness. Frictional effects between the puck, rod, and floor, as well as frictional effects in the pivot, are small enough to be considered negligible. Okay, so we have diagrams in each of the cases, and based on the fact that we're dealing with an angle here, I'm probably looking at some type of conservation of angular momentum. Okay, because I have a collision that results in rotation. Now, you might be thinking, why can't we also talk about linear momentum? Well, the thing is that the linear momentum of this system is actually not going to be conserved. The reason why is this pivot exerts an external force, which means momentum linearly is not conserved, okay? But angular momentum can still be conserved because this pivot is on the axis of rotation, which means the net torque acting on the system is going to be 0. Okay? So we can have conservation of angular momentum without conservation of linear momentum. Okay, so those are our different cases. On the graph below, we want to sketch and label the two quantities as a function of time for case 1. So this is the bouncing case. Okay, so we don't need to calculate values for the y-axis, but the same vertical scale should be used for both quantities. And remember, we want to conserve angular momentum. So it says we need to graph the angular momentum of the puck and the rod. I'm actually going to start with the rod because the rod remains at rest. So my graph from 0 to Tc for the rod is actually super easy. And then after the collision, the rod is moving in the forward or positive direction, so I'm going to give it some forward or positive momentum. Okay? And we can have that change occur immediately, or if you want to have it more realistic, you can have the change occur over, here, let me do this, over a small time period like so. Okay? Whatever is going to work best for your brain. Okay, so now we need to do the angular momentum of the puck. Now remember, angular momentum has to be conserved before and after the collision. So whatever our angular momentum total is before the collision, that has to equal the angular momentum total after the collision. So right now our angular momentum of the rod is 0 before, and afterwards is a positive 3. Okay, so when I have, or draw rather, the angular momentum from the puck, I want to make sure that I'm able to conserve momentum. So what I might do is I might make the puck have an angular momentum of 2 initially, and that's a dashed line. Now, in order for my angular momentum to be 2 afterwards, this value here has to be a -1. Which makes sense because this negative means that the puck is bouncing back. Okay, so I'm going to make sure that the collision occurs over the same time period, and then the puck moves backwards with an angular momentum of -1. Okay, so let me just highlight those so they become a little bit better. So again, the rod is at 0. Because it's at rest, and then it's gonna pop up to some positive value because we're moving in the forward direction. The puck, on the other hand, starts with some positive angular momentum and then that positive angular momentum becomes negative because the puck is bouncing backwards. The values I chose are based off of the fact that we need to conserve angular momentum. So my total value here is 2, and my total value here is also 2, keeping in mind that angular momentum is a vector. Okay. Then we want to rank the magnitudes of the 3 angular displacements, theta 1, theta 2, and theta 3, through which the rod has rotated 2 seconds after the collision. Use 1 for the greatest, 2 for the next greatest, and so on. If any 2 or all 3 angles are the same, use the same number for their ranking. In a clear and coherent paragraph, length response that may also contain figures and or equations, justify your ranking. Okay. So I'm going to kind of work without ranking first. So my largest angle is going to come from my largest angular velocity of the rod. Okay. So the largest angular velocity of the rod is going to come from the largest change in angular momentum of the rod. Largest change in angular momentum of the rod occurs with largest change in angular momentum of the puck, keeping in mind that when angular momentum is conserved, the angular momentum change of the puck is equal and opposite to the angular momentum change of the rod. Okay, so when does that largest angular momentum change happen? Well, when we have a large change in angular velocity, because remember, L is I omega, and this I is really going to stay the same for the puck. Okay, when does large changes in angular velocity happen? Well, remember, angular velocity is a vector, so that's going to happen with a change in direction. Okay, so what that means is the case that has a change in direction, based on this kind of flow chart that I just drew, is going to have the largest angular displacement of the rod. And that's going to happen in case 1. Okay. So without changing direction, the next largest change in angular velocity is going to come if we come to a stop, because you're essentially losing all of the angular velocity of the puck. And that happens in case 2. And then third and finally, the smallest, the smallest change in angular velocity comes when the puck simply slows down. And that happens in case 1. Okay? Remember, angular velocity, the things we have to keep in mind, is a vector, and that change in angular velocity is angular velocity final minus angular velocity initial. Now you might be thinking, Narc, the puck is moving linearly, how can it have an angular velocity? Remember, the angular velocity of the puck can be found by doing its linear velocity and dividing by the distance from the axis of rotation, r. Okay, so whenever we have a change in the linear velocity, we're going to have a change in that angular velocity, because r is not going to change. Okay. So now I need to put this flow chart into a paragraph form, and I'm essentially going to organize my paragraph exactly like this flow chart. So I'm going to start with saying that the largest angular displacement of the rod will occur with the largest angular velocity of the rod. Now, the few of these that I had already graded, I noticed students were not making this connection. They were not connecting the fact that a large angular displacement comes from a large angular velocity. Okay? That is an important point that you have to put in there, because you have to say why you're able to make this claim that case 1 is greater than case 2. And that claim comes from largest angular velocity. Okay? So the largest angular velocity of the rod comes from the case with the largest change in momentum of the rod. Okay. Now, remember, when we're doing problems with collisions, we want to focus in on momentum, not energy. That's another big mistake that I'm seeing in ones that I've graded is people are talking about energy, but this problem really isn't an energy problem. Okay. So the largest angular velocity of the rod comes from the case with the largest change in momentum of the rod. Angular, I should have said change in angular. I want to be specific. Angular momentum is conserved. So the change in angular momentum of the rod is equal and opposite to the change in angular momentum of the puck. So larger delta L for the puck means larger delta L for the rod. The change in angular momentum of the puck is largest when the puck changes direction because angular velocity is a vector, and case 1, and in case 1, the puck bounces back. The lowest change in omega occurs in case 3 when the puck only slows down. Therefore, got to wrap it all up. Therefore, case 1 will have the largest theta. Case 3, the smallest. Okay. Now, the way we've talked about answering this in class is also talking about how, or instead of thinking about like a change in angular momentum, we've also talked about like a conservation of angular momentum root, and the sense that initially the angular momentum of the puck was positive. So after, the angular momentum of the system still must be positive. Okay? When the puck bounces, that creates a negative angular momentum of the puck, which means the rod must have a really big forward positive momentum to keep the momentum of the system positive. Okay? You can also talk about how, because of conservation of momentum, so this is the bounce, when they stick together, okay, you can talk about how when they stick together, the initial angular momentum is shared by both the rod and the puck, essentially combining their moments of inertia, which leads to the lowest angular velocity because the puck is still moving forward, so the rod does not have to move as fast. Okay, so you can kind of go either way with answering this question. Okay, so let's take a look at the scoring guide. So for part A, we get 1 point for labeling a graph of a puck with an angular momentum that's non-zero, constant before TC, and constant that's in the opposite direction and smaller in magnitude. I did that. Okay. And then I get 1 point for labeling a graph of the angular momentum that's 0 and constant after TC that's opposite in sign to the puck's post-collision. I did that. And changes by amount that indicates no change in angular momentum of the rod-puck system. So essentially that we conserved angular momentum as well. So here's their example response. So I went from 2 to -1 and the rod had a value of 3 afterwards. They went from the puck having a value of 3 to -1, which meant the rod had to have a value of 4 initially. Or sorry, after the collision. Okay. So let's check out the paragraph points. So we get 1 point for indicating that a greater angular speed after the collision corresponds to the greater angular displacement. Like I said, that statement is very important. It seems like a very intuitive statement that you might not have to say, but you do have to spell it out explicitly. Okay, then we get 1 point for stating or implying that in all collisions, the angular momentum lost by the puck is equal to the angular momentum gained by the rod. So this is also the idea of conservation of angular momentum. We get 1 point for a valid argument stating that the puck's change in angular momentum is greatest in case 1, so the rod's change in angular momentum must also be greatest. Again, you can earn this point by talking about how when the puck bounces back, that leads to a larger negative momentum, so the rod has to have a greater positive momentum to keep the total angular momentum positive. And then you get 1 point for a valid argument about why the rod's angular momentum is greater in case 2 than in case 3. Okay? So essentially, why does the stick lead to a less angular velocity than the stop? And then, of course, our last point is for a logical, relevant, and internally consistent thing. So you wrote a good paragraph. So their example response is, all of the angular momentum of the puck is transferred to the rod in case 2. Since the rod has a greater angular momentum than in case 3, it must be traveling at a greater angular velocity. Oh, so this is that example response goes with this point up here. Okay. Or you could say because the puck is still traveling in the same direction in case 3, its change in momentum is less, therefore the increase in the rod's angular momentum is less. Okay. And that is the end of this solutions video. If you have questions, please, of course, do not hesitate to reach out. I'm happy to answer them. I know angular momentum can kind of be tricky, and especially these questions with all of the bouncing and everything. So if you do have questions, don't hesitate to ask. See you soon. Bye.